Okay, in today's lecture we're going to cover the first part of the section 6.3 material on Taylor and Maclaurin series. So the goal of this section is to come up with a power series representation of a function which does not rely on us making use of the form of the sum of a geometric series. So recall in our last section, 6.2, we were representing functions as power series, and we sometimes had to differentiate or integrate a given function in order to put it in the form of the sum of a geometric series. So in this section, 6.3, we'll talk about another method for expressing functions in terms of power series, which does not require us to make use of that form for the sum of a geometric series. It allows us to express much more general types of functions as power series. So throughout this section, here's our problem that we're considering. Let's suppose that we want to represent some function, let's call it f of x, as a power series centered at x equals a. So our goal here is to take this function f of x that we're given and write it as a power series centered at a. So something of the form, the series from n equals 0 to infinity of c sub n times x minus a to the nth, since we're centered at a. Or if we were to write this out, we would have c naught plus c1 times x minus a to the first, plus c2 times x minus a squared, plus c3 times x minus a cubed, c4 x minus a to the fourth, and so on. So what we need to find here are the coefficients of this power series. What are the values of c naught, c1, c2, c3, c4, and so on? Or more generally, what is the general coefficient, c sub n, such that we could represent this function f of x in terms of that power series. So in order to do this, we're going to evaluate the function and some of its derivatives at a, and that will allow us to solve for these coefficients. So as an example, let's think about if we were to evaluate our function at x equals a. So if we were to substitute x equals a into this equation, our function f evaluated at a would be given by the following. So let's look at what happens when we plug in x equals a to our power series. So this first term, c naught, stays there. It's a constant, so we have c naught. And then each other term following this involves some power of x minus a. Say x minus a to the first, x minus a squared, x minus a cubed, and so on. So when we plug in x equals to a, all of these terms become 0. And we're left with just c naught. So here we have solved for our first coefficient. C naught is equal to the value of our function at x equals a, whatever value we want our power series centered about. So if we want to find our next coefficient, c1, well, we could differentiate our function f of x. We have f prime of x would then be c1 plus 2c2 times x minus a to the first power plus 3c3 x minus a squared plus 4c4 x minus a cubed, and so on. That is, we differentiate the power series that we expanded term by term. We saw we can do that from our theorem in the previous section. So if we were to evaluate this derivative, f prime at x equals a, well, we have our initial constant, c1, and then all of the subsequent terms involve some power of x minus a. So when we plug in a in place of x, all of these terms become 0, and we're left with just the constant term c1. So let's see if we can find our next coefficient, c2. So if I were to take my second derivative of this function, f double prime of x, I would have 2c2 plus 3 times 2, c3, x minus a to the first power, plus 4 times 3, c4, times x minus a squared, and so on. So again, if we evaluate this second derivative at x equals a, well, we have the initial term, 2 times c2, which is a constant, and every subsequent term involves some power of x minus a. So when we evaluate this second derivative at x equals a, all of these later terms involving a factor of x minus a become 0, and we're left with 2c2, which implies that c2 is equal to the second derivative of our function at x equals a divided by 2. So if we were to keep differentiating, let's look at what we have for f triple prime of x. F triple prime is given by 3 times 2, c3, plus 4 times 3 times 2, c4, times x minus a to the first power, and so on. So evaluating this third derivative at x equals a, we have our initial term, 3 times 2, c3, and then every subsequent term is going to involve some power of x minus a to the first, squared, and so on. So when we evaluate this function at x equals a, all of those x minus a terms become 0, and we're left with just this initial term. That is 3 times 2, c3. So solving for c3, we have f triple prime of a divided by 3 times 2, which we could think of as f triple prime of a divided by 3 factorial. Now looking back at our earlier terms, let's see if we can establish a pattern that's appearing. So we found that c3 would be the third derivative of f at a divided by 3 factorial. c2 is the second derivative of f at a divided by 2, which is the same as 2 factorial. So we have f double prime of a over 2 factorial here. For the term before that, we had c1 was equal to f prime of a, which is the same as f prime of a divided by 1 factorial. So if we were to repeat this process, we keep seeing the same pattern emerge. So we can say that in general, the coefficient for the nth term of my series, that is c sub n, would be given by the nth derivative of my function, evaluated at x equals a, divided by n factorial. So once we found an expression for our c sub n coefficient, we can substitute that back into the general expression that we had for the form of our power series, and we see that the function f of x can be represented as the sum from n equals 0 to infinity of c sub n, which we just said is the nth derivative of f at a, divided by n factorial, times our x minus a to the nth power. So this power series representation of a function is what is called the Taylor series of that function, centered at x equals a. And the notation that we're using here, remember this superscript notation, f superscript n of a, where n is written in parentheses, is used to denote the nth derivative of our function f of x, evaluated at x equals a. So this Taylor series allows us to find a power series representation of a function without relying on that form for the sum of a geometric series. So let's look at some examples of this. In our first example, we are asked to find the Taylor series for the function f of x is e to the 3x, centered at 2, and then we're also asked for the radius of convergence of that series. So we just saw in our derivation for the formula for that Taylor series, we need to find an expression for the nth derivative of our function. So for any problem that asks us about Taylor series, we need to start by finding the first several derivatives of the function that we're given until we can establish a pattern. So let's start by saying here, if the function f of x is given by e to the 3x, then our first derivative, f prime of x, using the chain rule, is 3e to the 3x. Our second derivative would be f double prime of x. Again, using the chain rule, we would have 9e to the 3x. Our third derivative, f triple prime of x, using the chain rule, gives us 27e to the 3x, and so on. So we start to see a pattern emerging pretty quickly here. So we can say, in general, the nth derivative of my function is given by 3 to the nth power times e to the 3x power. So we see that for each of our derivatives, we always have a e to the 3x term. And the only thing that's changing out in front is the constant. For the first derivative, we had 3. For the second derivative, our constant was 9, or 3 squared. For the third derivative, we had 27, or 3 cubed. So in general, for the nth derivative, we have 3 to the nth power. Now, once we have an expression for the nth derivative, we're supposed to evaluate it at x equals a. Now, in this example, we were told that our power series was supposed to be centered at x equals 2. So we replace x by 2, and we're left with 3 to the nth power times e to the 3 times 2, or e to the 6th. Now, once we have this expression for our nth derivative of the function evaluated at our center point, we have the Taylor series of that function. In this example, f of x is the sum from n equals 0 to infinity of our nth derivative evaluated at 2, which we just found to be 3 to the nth power times e to the 6th, divided by n factorial, times x minus a, which in this case our power series was centered at 2, so we have x minus 2 raised to the nth power. So this would be the Taylor series for that function centered at 2. Now, in the last part of this example, we're asked to determine the radius of convergence. So recall that most likely, if we're asked for the radius of convergence of a power series, we're going to make use of the ratio test, which says that we would look at the limit as n approaches infinity of the absolute value of the ratio of our n plus 1 term to the nth term. So here, our n plus 1 term would be 3 to the n plus 1 times e to the 6th, divided by n plus 1 factorial, times x minus 2 to the n plus 1 power. and then we divide by the nth term. But as usual, our nth term is a fraction, so dividing by that fraction is the same as multiplying by its reciprocal, which would be n factorial over 3 to the nth times e to the 6th times x minus 2 to the nth. So let's see which terms can cancel here. Here we would have an e to the 6th in the numerator and denominator, which cancel directly. Our factor 3 to the n plus 1 divided by 3 to the n leaves us with a constant 3 out in front. So we have the limit as n approaches infinity of 3 in our numerator. Let's see what else. We had a factor of x minus 2 to the n plus 1 over x minus 2 to the nth. So if we cancel n factors, we're left with a x minus 2 in the numerator. And then lastly, our n factorial divided by n plus 1 factorial leave us with an n plus 1 in the denominator. So here, simplifying a little, we can pull the absolute value of 3 times x minus 2 out in front of our limit, since it doesn't depend on n, and we're left with the limit as n approaches infinity of 1 over n plus 1. And we know that as n approaches infinity, this limiting value of 1 over n plus 1 is 0. So we get a limit of 0, which is less than 1. And notice that we get that limiting value of 0 regardless of what the value of x is. It doesn't matter what this constant was out in front of the limit, since this limiting value is 0. So any constant that we had out front multiplied by 0 leaves us with 0, which is less than 1. So we can say this holds for all values of x, which are real numbers. So we can say here that the radius of convergence is given by r equals infinity. That is, this power series converges for every value of x. Or in other words, no matter what value of x we choose, we can represent e to the 3x in terms of the power series that we found above. So let's look at some other ones. In our next example, we've got the same sort of problem. We want to find the Taylor series for 1 over x centered at 3 and determine the radius of convergence. So if our function f of x is given by 1 over x, we know that to find a Taylor series, we need to find an expression for the nth derivative of this function. So our first step is going to be to find the first several derivatives until we can see a pattern emerge. So here, for f of x given by 1 over x, or x to the negative first, we would have f prime of x is negative 1 over x squared, or negative x to the negative 2 power. The second derivative, f double prime of x, would be positive 2 over x cubed, or 2 times x to the negative third. And our third derivative, f triple prime of x, would be given by negative 6, or negative 3 times 2, times x to the negative fourth, or divided by x to the fourth. And we start to see a pattern emerging here. So let's see if we can come up with a general expression for the nth derivative. So looking at the terms that we found here, let's consider the numerator and denominator separately. So we see that our denominator for the first derivative is x squared. For the second derivative, we had x cubed. For the third derivative, we had x to the fourth. And that pattern will continue. So in general, for our nth derivative, our denominator would be x to the n plus 1 power. That is, the power of x is always 1 greater than the order of the derivative. Now, we see, looking at the numerator for each of these terms, that they're alternating in sign. Our first derivative was a negative, our second derivative was a positive, third derivative was a negative, fourth derivative will be positive, and so on. So in general, we have -1 to some power to capture that alternating sign. And let's think about which order derivatives we want to be negative. So here it was the first, the third, the fifth, so all of the odd ones should be negative. So we're going to take -1 to the nth power. So if n is odd, we have a -1. If n is even, we have a +1. Now lastly, capturing the constant in the numerator. Well, for our first derivative, we had a 1. For the second derivative, we had 2. For our third derivative, we had a constant of 6, or 3 times 2. So in general, for our nth derivative, we have n factorial for our numerator. So once we have an expression for the nth derivative of our function, we're supposed to evaluate that expression at the given value of x. In this case, we wanted a power series centered at 3. So plugging in 3 for x, we have -1 to the nth times n factorial over 3 to the n plus 1 power. So now that we've found this, we have the formula for our Taylor series. So here, the Taylor series for f of x would be the sum from n equals 0 to infinity of this nth derivative term that we just found, which was -1 to the nth times n factorial over 3 to the n plus 1 power times x minus a, which was 3 to the nth. And then recall, if we look back at our definition, this nth derivative term that we found has to be divided by n factorial. So going back to the series that we had, this term out in front still has to be divided by n factorial. So notice that when we do that here, the n factorial term that we had from our nth derivative and the n factorial term from the formula for our Taylor series will cancel, and we are left with the sum from n equals 0 to infinity of -1 to the nth times x minus 3 to the nth all over 3 to the n plus 1 power. So this would be the Taylor series for that function centered at 3. And then the question is, what is the associated radius of convergence? So to determine the radius of convergence for a power series, we might again use the ratio test. So we look at the limit as n approaches infinity of the absolute value of the ratio of our n plus 1 term to the nth term. So here we have -1 to the n plus 1 times x minus 3 to the n plus 1 all over 3 to the n plus 2. And then we divide by the nth term, which was a fraction, so equivalently we multiply by its reciprocal, which was 3 to the n plus 1 over -1 to the nth times x minus 3 to the nth. So that leaves us with the limit as n approaches infinity of the absolute value of, well, let's see which terms cancel. So here we had a -1 to the n plus 1 over -1 to the nth. So canceling n powers of -1, we are left with a -1 for our numerator. We also had a 3 to the n plus 1 over 3 to the n plus 2. So canceling n plus 1 powers, we have 1 power of 3 left in our denominator. And then looking at the last terms, we had an x minus 3 to the n plus 1 over x minus 3 to the nth. So canceling n powers, we have x minus 3 to the first for our numerator. So this leaves us with a limit of, as n approaches infinity, of the absolute value of x minus 3 divided by 3. And notice that this does not depend on n. That is, it is a constant with respect to n. So as n gets larger and larger, we always have the same value of our function, absolute value of x minus 3 over 3. And making use of the ratio test, we can say the series converges if this limit, that is the absolute value of x minus 3 over 3, is less than 1, which means that the absolute value of x minus 3 is less than 3, so our radius of convergence is 3. So we see here that the Taylor series for 1 over x centered at x equals 3 was this power series that we found earlier in our example. And the function 1 over x can be represented by that power series as long as the distance that we have moved from x equals 3 is less than 3 units. So we could move from 0 to 6 here and still have convergence of that power series, but possibly not including the endpoints. So let's look at another one. In our next example, we've got a very similar problem. We want the Taylor series for the function natural log of x centered at 1 and the associated radius of convergence. So as with our earlier examples, if our function f of x is given as log x, we want to find the first several derivatives until we can establish a pattern. So here, our first derivative, f prime, is 1 over x. Our second derivative would be -1 over x squared. The third derivative would be a +2 over x cubed. As we start to see a pattern emerging, maybe it's not clear just yet, but it's starting to look similar to what we saw in the previous example. So if we keep going, our fourth derivative would be given by -6 over x to the fourth. The fifth derivative would be given by a +24 over x to the fifth, and so on. So now it's a little clearer what our pattern is. So in general, let's see if we can find this nth derivative. So again, looking at the numerator and denominator separately, let's consider the pattern in the denominator first. For our first derivative, f prime of x, our denominator was x. For the second derivative, it was x squared. For the third derivative, x cubed. Fourth derivative, x to the fourth. Fifth derivative, it was x to the fifth. So in general, for the nth derivative, we would have x to the nth power as our denominator. Now we see, looking at these first few terms in our first several derivatives, that they are again alternating in sign. Our first derivative was positive, the second derivative was negative, third was positive, fourth was negative, and so on. So to capture the alternating sign, we're going to take -1 to some power, and let's ask ourselves which terms were negative. Here it was all of the even-ordered derivatives, so we're going to take -1 to the n plus 1, so that if n is even, we have an odd power of -1, which would make it a negative. And the last term that we have to capture is the constant in our numerator. So here for our first derivative, we had 1. For the second derivative, we had 1. For the third derivative, we had 2. For our fourth derivative, we had 6, or 3 times 2. For the fifth derivative, we had 24, which is 4 times 3 times 2. So in general, the pattern in our numerator is in -1 factorial. So for our third derivative, we had a constant of 2, or 2 factorial. For the fourth derivative, it was 6, or 3 factorial. So in general, for the nth derivative, we have negative, or n-1 factorial. And once we find this expression for our nth derivative, we're going to evaluate it at the given value x equals a. In this case, x equals 1. So we have -1 to the n plus 1 power times n-1 factorial divided by 1 to the nth power. So that is -1 to the n plus 1 times n-1 factorial. So once we have this expression, we can substitute into the formula for our Taylor series, and we have f of x would be the sum from n equals 0 to infinity of -1 to the n plus 1 times n-1 factorial divided by n factorial, all times x minus a, which in this example a was 1, raised to the nth power. So let's see how we can simplify here. We find that we have an n-1 factorial over n factorial, which is just one term greater than that n-1. So simplifying, we have f of x is the sum from 0 to infinity of -1 to the n plus 1 over n times x minus 1 to the nth power. Now, one thing that we have to be a little bit careful of here is the starting value of our index. So if we had substituted into the formula for our Taylor series without thinking about the starting value of the index, what we're left with is a summation starting at n equals 0. But notice that we have a division by n in the nth term of our series. So that first term corresponding to n equals 0 would be undefined, since we would have division by 0. So I claim that really the Taylor series should be the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 1 to the nth over n. So why am I allowed to ignore that first term corresponding to n equals 0? Well, let's recall the reasoning. So that initial term corresponding to n equals 0, which gives us c0, remember, is supposed to equal the value of our function f at whatever x value we were given. In this example, x equals 1. Now here, our function f of x is natural log of x. So evaluating at 1, we have the natural log of 1, which is 0. So the 0th term in our series does not appear. It has a 0 value, which is why I'm allowed to change my starting value from 0 to 1 without manipulating the general term of my series. So here a little bit tricky because the value of our function natural log x at the given x value of 1 is itself 0. So that means that 0th term is not appearing. Now to find the radius of convergence for this power series, we apply the ratio test. So we would have the limit as n approaches infinity of the absolute value of -1 to the n plus 2 times x minus 1 to the n plus 1 all over n plus 1 divided by the nth term, or equivalently multiplying by n over -1 to the n plus 1 times x minus 1 to the nth. So that leaves us with the limit as n approaches infinity of the absolute value of, let's see which terms are left. So we had a -1 to the n plus 2 over -1 to the n plus 1. So canceling n plus 1 powers, we have a factor of -1 in the numerator. For our x minus 1 to the n plus 1 over x minus 1 to the nth, we cancel n powers, and we're left with x minus 1 to the first in our numerator. And then the remaining terms, n divided by n plus 1, don't simplify, so we have an n in the numerator, n plus 1 in the denominator. And simplifying this, well, we can pull the absolute value of x minus 1 out in front of our limit, and we have the limit as n approaches infinity of n over n plus 1, and the limiting value here would be 1. So we're left with just the absolute value of x minus 1. Now for convergence, we know that this limiting value would have to be less than 1 by the ratio test. So our radius of convergence here is 1. From our centering value, 1, we can move 1 unit to the left or the right and still have convergence for this power series. Perhaps including the endpoints, perhaps not. So now that we've had a few examples of finding Taylor series of a function centered about a given point, we'll talk about a specific Taylor series, which is a little simpler to work with, known as the Maclaurin series for a function. So let's start by defining it. Here, the Maclaurin series for a function f of x is defined as the Taylor series for that function centered at 0. So that is, f of x is the sum from 0 to infinity of the nth derivative of our function evaluated at 0, since 0 was the value where we're centering our power series, divided by n factorial times x minus 0, or just x to the nth power. So Maclaurin series for certain types of functions have some very nice applications, which we'll see a little bit later in this section. But let's look at an example of finding a Maclaurin series. So in our first example, we are asked for the Maclaurin series for e to the x and determine its radius of convergence. So if we're asked for a Maclaurin series of a function, again, that's just asking for the Taylor series of that function centered at 0. So these problems are really the same as what we've been considering. So let's look at an example here. If our function f of x was e to the x, we just want to find the first several derivatives until we can establish a pattern. So recall that the first derivative of e to the x is e to the x. So the second derivative would also be e to the x. And the third derivative is also e to the x. In fact, every higher derivative gives the same function, e to the x. So we can say, in general, the nth derivative of the function e to the x is itself, e to the x power. And so if we were to evaluate this nth derivative at the given x value where we're supposed to center, and here, since we're asking for a Maclaurin series, we're talking about the Taylor series centered at 0, well, we would have e to the 0 power, or 1. So to find our Maclaurin series for f of x, which was e to the x, we would be taking the sum from n equals 0 to infinity of our nth derivative evaluated at 0, which we just found to be 1, divided by n factorial times x minus 0, or just x, to the nth power. Or to be a little more concise, we might write this as the sum from 0 to infinity of x to the nth power over n factorial. So this is the Maclaurin series for e to the x, and let's see where that is a valid representation of the function e to the x. So to find the radius of convergence, we would look at the limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 factorial, divided by our nth term, or equivalently multiplying by its reciprocal, n factorial over x to the nth. So this gives us the limit as n approaches infinity of, well, we have x to the n plus 1 over x to the nth. So canceling n powers, we're left with x for our numerator. And then we have an n factorial over n plus 1 factorial, which reduces to 1 over n plus 1. So taking the absolute value of x out in front of our limit, we have the limit as n approaches infinity of 1 over n plus 1. And this limiting value, as n gets larger, is 0. So we get a limit of 0, which is less than 1, for all values of x, which are real numbers. So that is, this Maclaurin series converges over the entire real line. So our radius of convergence, r, would be infinite. So in other words, we see that the function f of x equals e to the x can be represented by this relatively simple power series, no matter what the value of x. So I'll make a note here in the lecture, or I would encourage you to make a note beside this example, maybe put a star beside it, and as a note to yourself, you will want to have this memorized. That is, you want to memorize the form of this Taylor series for e to the x. And we'll see why you'll want to have this Taylor series memorized a little bit later in this section. It turns out that we can find Taylor series for certain related functions very easily, as long as we know the Maclaurin series for e to the x. So in the next part of this lecture, we'll talk about some Maclaurin series for other common functions and start to talk about their applications.